Welcome to The Explainer. I'm your host, and today we're taking a fascinating journey from powder to the perfect pill. We're going to uncover the hidden science of pharmaceutical manufacturing and look at how drug developers actually turn raw materials into precise, life-saving tablets. Okay, let's dive into this.
Have you ever just stopped to wonder how loose, dusty powder somehow transforms into a solid, tamper-proof medication? I mean, guaranteeing that a powdery mix becomes a perfect pill every single time is actually a massively complex physics and math problem. It's not just, mixing chemicals in a beaker. It's about engineering a physical structure that can survive manufacturing, survive packaging, and transport across the world, only to break down at the exact right moment inside the human body. To really understand this, think of it like baking a cake. You can't just take the active pharmaceutical ingredient, or the API as it's called, and compress it on its own. It needs very specific helper ingredients to work properly. These are called excipients. Just like a recipe, you need binders to actually hold the whole thing together, diluents like lactose to add bulk, disintegrants so it dissolves later, and lubricants so it flows smoothly. It really is a highly specific matrix. But what happens when you get that recipe wrong? Well, in the pharmaceutical world, the cost of physical trial and error is literally staggering. APIs are incredibly expensive. We're talking thousands of dollars per gram during early development, and researchers usually only have tiny amounts to work with. If a mixture doesn't compress right, say the tablet crumbles or it sticks to the machine, or maybe it's just too hard to dissolve, scientists have to scrap that entire batch and start over. That wastes precious materials, burns through millions of dollars, and worst of all, it significantly slows down getting new drugs to the patients who need them. So to appreciate just how delicate this recipe is, we have to transition from the chemistry side of things over to the sheer physical brute force of manufacturing. The actual physical making of a tablet on a rotary press happens in 4 rapid mechanical steps. First, the powder drops in and fills a mold called a die. Second, a bottom punch moves up to adjust the powder weight, essentially kicking out any excess. Third, the top and bottom punches come together and compress the powder. And finally, step 4, the top punch pulls back, and the lower punch pushes that newly formed tablet up so it can be ejected.
Now, what's really interesting about this slide is the incredible mechanical stress happening right in the middle, at stage 3. Look at how the top and bottom punches are being driven right into the die. In a real manufacturing plant, these punches pass between heavy rollers that use immense mechanical force to physically crush the powder together. We are talking hundreds of megapascals of pressure, all happening in mere milliseconds. It is a violent physical event for those little powder particles.
And under that immense pressure, the powder particles don't just sit there, right? They undergo extreme physical deformation. Some materials go through what's called elastic deformation. They squash down under the pressure, but then sort of bounce back to their original shape, which, as you can imagine, might cause the tablet to crack open later. Other materials undergo plastic deformation, meaning they permanently mold and lock together, kind of like clay. And then others experience brittle fragmentation, where the particles literally shatter into smaller pieces under the force. So making the perfect tablet requires a very careful balance of all these behaviors.
Because of all these intense physical forces, the initial powder has to have absolutely perfect properties before it ever even hits the press. Variables like particle size and shape, the surface area, the density, the strength of the granules, and even just how well the powder flows, these will literally make or break the final tablet. I mean, if a powder is too dense, it might need way too much force, which messes up how the drug dissolves later. If it doesn't flow well, your tablet weights are going to be all over the place. All of this leads us to the ultimate question. How do we predict manufacturing success without wasting all those materials?
Well, the answer lies in a vital metric called tabletability. This is basically the holy grail metric of pill making. By definition, tabletability is the relationship between tablet tensile strength, which just means how strong and resistant to breaking the tablet is, and compaction pressure, which is the amount of force the machine is applying. Simply put, it's a direct measure of how tough a tablet becomes when a specific amount of pressure is applied to that powder.
So, the crucial point is this. If researchers can predict a powder's tabletability mathematically, they can completely skip that wasteful physical trial and error phase. Instead of mixing batches, pressing them, breaking them in a lab just to see what works, they want to move from mechanical brute force straight into digital prediction. They want an algorithm to just tell them if a specific blend of excipients and API is going to result in a robust tablet long before they ever physically touch the powder.
And this brings us to a major breakthrough, the Vreeman-Sun tabletability equation. This mathematical model beautifully describes tabletability data using just 3 distinct parameters. First up is sigma max, which represents the absolute maximum achievable tensile strength of the tablet.
Second is alpha, which dictates how the curve shifts along the pressure axis. And third is beta, a parameter deeply tied to the powder's plasticity. If scientists can predict these three things for a mixture, they can predict exactly how that mixture will compress into a perfect pill.
But of course, here is the ultimate challenge. Drugs are almost never just one pure powder, right? They're complex blends. So the question is, can we use mathematical mixing rules to accurately predict how a blend of two different powders will behave, purely based on knowing the tabletability of their pure forms? To figure this out, researchers tested three main mathematical models: the linear mixing rule, the harmonic mixing rule, and the power law mixing rule.
To test these mathematical rules in the real world, researchers gathered up a huge variety of pure ingredients to assess their individual tabletability. Notice the highly plastic materials on the left, like microcrystalline cellulose. See how their curves shoot up and then kind of plateau? That shows they densify really easily under pressure. Now, on the right, we have hard materials. Their lines are much flatter, meaning they resist compaction and really don't densify easily. The researchers then took these vastly different materials and mixed them together.
And this brilliantly illustrates what happened when they looked at the results of one of those mixtures, a blend of 60% plastic material and 40% hard material. The dots you see represent the actual physical experimental data. Now look at the dashed lines representing the mathematical predictions. The blue dashed line, that's the linear rule. It vastly overestimates the tablet's strength at higher pressures. The red dashed line, the harmonic rule, it significantly underestimates the strength. But look at that green dashed line. The power law mixing rule perfectly hugs the experimental data points. It accurately predicted the physical reality using purely math.
Just to prove this wasn't some lucky fluke, the scientists quantified the error across tons of different types of blends, using something called the mean absolute scaled error. Basically, the lower the bar, the lower the error. And whether they were mixing plastic and hard materials, or two plastic materials together, or even two hard materials, the power law model, which is represented by the green bar here, consistently had the lowest error. In fact, in 10 out of the 13 complex binary mixture systems they tested, the power law model was the clear absolute winner.
So why does all this math actually matter to you and me? Well, as the researchers note, accurately predicting mixtures is a significant step toward achieving digital tablet formulation design. What this means is that pharmaceutical companies can start using computer models to screen thousands of potential formulations entirely digitally. By knowing exactly how ingredients are going to behave together before they ever hit the manufacturing floor, we can develop life-saving drugs so much faster, significantly cheaper, and with a much higher guarantee of quality.
It is pretty incredible to think that the humble little tablet sitting in your medicine cabinet right now represents an absolute triumph of advanced physics and mathematical prediction. By taming the brute force of mechanical presses with the elegance of the power law equation, science has made drug manufacturing incredibly efficient. But it does leave us with a fascinating, provocative question to end this explainer on. If algorithms can now digitally design the perfect structurally sound pill without physical trial and error, what other complex, everyday manufacturing processes will mathematical modeling conquer next? Thanks so much for joining me on The Explainer, and keep questioning the world around you.